Hello and welcome to the first video of geometric progression. In this video, we will cover about the theory part of geometric progressions. So let's get started. The definition is that a succession of numbers is said to be in GP if the ratio of any term and the preceding term is constant throughout. Now, for AP, it was difference, and for GP, it is ratio. Now this constant term is known as common ratio of the GP. Now let's try to find out another term of a GP. So we let A to be the first term and R to be the common ratio of the GP. So the first term of GP would be T1 is equal to A, and the second term will be T2 is equal to AR, because R will get multiplied with T1, because that's what our definition is. And T3 will be AR square. So proceeding this way, we see that for T1, the power of R is 0, for T2, power is 1, for T3, power is 2, so for Tn, power would be n minus 1. So our nth term would be AR to the power n minus 1. Now let's look at the GP. So before we look at this, let me give you some examples of GP. So for example, if R is 2 and first term is 1, then it will go like this: 1, 2, then 2 square, 1 into 2 square, that is 4, then 1 into 2 to the power 3 or 2 cube, that would be 8, 1 into 2 to the power 4, that would be 16, and so on. If the R is 3 and A is 1, then it would be 1, then 1 into 3, which is 3, then 1 into 3 square, which is 9, then 1 into 3 cube, that is 27, then 1 into 3 to the power 4, which is 81, and so on. Now, let's look at the properties of a GP. If each term of a GP is multiplied with a non-zero number, then the sequence thus obtained is also in GP. So we have assumed that AR square, AR cube is a sequence in GP where A is the first term and K is the common ratio. Now we multiply this sequence with a non-zero number, let's say K. Then it becomes AK, ARK, AR square K, AR cube K. So we see that if we multiply with some constant K, then the resulting geometric progression has first term as AK, but the common ratio does not change. It remains R. Now, similarly, when you will divide a GP with a constant number K, which is non-zero, then the first term will change to A by K, second term will change to AR by K, third will change to AR square by K, and so on. But the common ratio will not change. Only the first term and only the terms will change by a factor of K, but common ratio will not change. The third one says that the reciprocal of the terms of GP are also in GP. So if the GP is A, AR square, AR cube, then the reciprocals are 1 by A, 1 by AR, 1 by AR square, 1 by AR cube. And then we can quickly see that the first term is 1 by A and common ratio is 1 by R. Now we try to find out the sum of n terms of a GP. So as always, A is the first term and common ratio is R. And we let that Sn is the sum of first n terms. So first case is that when R is not equal to 1, then we write the value for Sn and then we multiply it with R and we rewrite the value again. So if you see that if we subtract this, the left hand side will become 1 minus R into Sn. AR will get cancelled of top and bottom, AR square will get cancelled, and up to Tn it will get cancelled for the top series, and for the bottom one it will get cancelled up to Tn minus 1. So up to AR to the power n minus 1 terms will get cancelled, And then we will be left with a minus ar to the power n. So we see that sum of n terms is a into 1 minus r to the power n by 1 minus r, or ar to the power n minus 1 by r minus 1. But what if r is equal to 1? Then in this case, you have sum of series is, if you substitute literally r is equal to 1 in this, then you will get a into 0 by 0. Now 0 by 0 is indeterminate, so until we go to calculus, I will not explain that how to resolve that problem. I mean, I can tell, but I will rather hold on to that. So for this simple case, Sn will become a plus a plus a up to n terms equal to na. Now, if modulus of r is less than 1, we can find out the sum up to infinite terms. And what will happen is that r to the power n will become 0 if modulus of r is less than 1. So our sum of infinite terms of the GP will be a by 1 minus r. Now we look at an example of a recurring decimal, which is an example of an infinite GP. So for example, we look at something like zero point 0.3 bar or 3 dot. So it's a recurring decimal which is fundamentally rewritten as 0.3333 up to infinity. An example of this would be 1 by 3 or 3 by 9. Or rather 2 by 6 also will also work, I guess. So 1 by 3, 2 by 6, 3 by 9, 11 by 33, anything which resolves to 1 by 3 will work for this. So we can write this as zero point 0.3 plus 0, 0.03 plus 0.003 and so on. So it will be 3 by 10 plus 3 by 100 and so on. We take 3 by 10 common and we have 1 plus 1 by 10 plus 1 by 100 up to infinity. So we have first term as 1 and common ratio is 1 by 10, which is less than 1, and modulus is definitely less than 1 of 1 by 10. So we can apply the formula of infinite series GP. So that will be 1 by 1 minus r, and then we substitute the value as 1 by 3 as I've already said. Now, there are certain progressions where the sum of terms of an AP is multiplied with corresponding terms of a GP. And then this new series is called Arithmetico geometric series. So for example, there is an arithmetic series 2, 5, 8, 11, and there is a geometric series x plus x square plus x cube plus x power 4. And if you multiply the corresponding terms, you get 2x plus 5x square plus 8x cube plus 11x4 and so on. So how to find the sum of these kind of series? So you first write the value of s, then you take the common ratio of the GP and multiply that with x. In this case, that is x. And then you shift that by one term and rewrite it. So the x square term will be below x square, so it becomes 2x square below 5x square, 5x cube below 8x cube, and 8x to the power 4 below 11x to the power 4. When you subtract, you will obtain a geometric series starting from second term, and it may be first term also, but it depends what exactly the first term of AP is. If it is a nicely, or rather I should say, if it just for example, it could very well have been 3, 6, 9, 12, the arithmetic series, then we could have the 1 minus x into x starting from first. But in the worst case, you will have starting from second. So there you go. That's how we compute the sum of an arithmetic or geometric series. So with this, we come to an end of geometric progression theory, and starting from next video onwards, I will show you problems, and then we will see more of harmonic progression and all. But for now, it will be problems of geometric progression. So I hope you have enjoyed the video. If you have enjoyed the video, please do like the video. Thanks a lot for watching.